Hi, everyone. My name is Max Stritzinger. I'm an SRE at Bloomberg, and today I'm going to talk about integrating Kubernetes networking into bare metal or on-premise environments. So just kind of an overview of this talk. The first thing I'm going to go over is kind of the basics of Kubernetes networking. I'm going to talk about kind of what the options are for implementing that network model on-prem or on bare metal. I'm going to talk about our specific networking environment. So what our hosts look like, what our network looks like, and kind of how that creates some challenges in implementing some Kubernetes networking. And then hopefully, if I have time, I'm going to talk about some tips and some tools that you might be able to use to debug your own environments if you're doing this. So the first thing I want to do is I want to get on the same page around what the Kubernetes networking model is. So pods are our schedulable units of work. They all get an IP address, and the model says, among other things, that pods need to be able to communicate with each other. So there's no real spec on how you have to implement that. But in general, there's kind of two categories of implementations. So there are overlay networks, and then there's kind of more of a flat network model. And the distinction between these two is, does the rest of the network have knowledge of the pod IP space of the pod CIDR? And if the rest of the network does, then you're probably running with a flat network. If the rest of the network doesn't really have any knowledge of the pod IP space, then you're probably using an overlay. And I guess really the obvious difference here is that, if you're off cluster, if you can talk to a pod IP, then you're probably running a flat network. And if you can't, then it's probably an overlay. So in our environments, we have to support both. So I'm going to talk about that. But you might be wondering, what is required in order to implement these, right? So overlay networks, we need two things. We need encapsulation if we ever want to talk to a pod IP from a pod or a host in the cluster. So if we drop packets onto the wire with a destination address being a pod IP, the network's just going to drop that traffic on the ground because, again, in an overlay scenario, the network doesn't have any knowledge of the pod IP space. So what we do is we take that original traffic, the encapsulated traffic, and we put it in another protocol like UDP if you're doing VXLAN, or in an IP packet if you're doing IP and IP tunnels. And now the destination address on this encapsulating packet is going to be the host that the destination pod lives on. The source address is going to be the host that the originating pod lives on. And now we can pass that traffic. When it gets to the destination host will unwrap it and then pass it all kind of transparently to the pod. But if we want to have this going, we need kind of an agent that's running on all of our nodes that's programming these routes, that knows if a pod gets launched on a certain host, if any of the other hosts want to talk to that pod IP, then they need to encapsulate traffic to that host. So that's one of the things that we need for implementing an overlay network. The second thing that we need source NATing. If my pod wants to talk to the rest of the network, then again, if the source address is a pod IP, the traffic might reach the destination, but it's not going to be able to come back. So what we do is we take the host IP and we put that in place of the pod's address, and then the kernel will kind of keep track of this address translation that's happened. And on Linux, this is usually done using iptables Masquerade. Conversely, flat networks, we don't need encapsulation. We don't need source NATing, right? Because you can just talk directly to pod IPs. They're totally routable on the network. What you do need, though, is you still kind of need an agent that is sharing pod routes. So again, if a pod gets launched, we need some way of informing the rest of the network that this pod lives on this host and this is where the traffic should go. So you're maybe wondering, what should you choose? And I think there's probably pros and cons to each. So with overlay networks, you don't actually need to maybe engage your network team for these. So all you really need to implement an overlay is UDP connectivity or IP connectivity. But I'll put a little asterisk by that and come back to that later. You can reuse the pod IP space between clusters because, again, these are not real IPs. You don't have to worry about allocating out of your organization's range or something. And something else that I think is really nice about these is that the ingress points to your cluster are really well defined. So you've got node port services, you've got load balancer services, you've got host network pods, but it's really kind of obvious where traffic can come into your cluster, and that's not the case with flat networks. Some downsides, though, are that you are going to pay a little bit of overhead in terms of computation, in terms of space on the packet, in terms of encapsulation. So that's not so great. Also, if you have on the rest of your network source address space firewalls, all of your pod traffic is going to have the IPs of your host. So all of your pods are going to be as privileged or as unprivileged as your hosts are against those firewalls. So that may be something that you don't want or something that you do want, but something to consider. And also, this does kind of complicate debugging. So you have to be aware that the source NAT is happening or this encapsulation is happening if you're using a tool like tcpdump. To contrast, flat networks don't have that same issue. So if you're using tcpdump, everything kind of looks as you'd expect. So that's kind of nice. Also, pods can be talked to directly. So because they're routable on the rest of the network, you could imagine maybe a service discovery mechanism where we talk directly to pods. I'm not sure if I would do that, but something you could do. There's also lots of options for source address space filtering. So I mentioned before that with source natting, everything is as privileged as your host, but in a flat network, we can kind of choose, depending on what your network provider is, we can kind of choose which IP ranges we want to drop pods into. And so that can kind of make them more or less privileged against those hosts or those source address space firewalls. The downside of this is that you definitely are going to have to talk to your network team because these are real IP addresses on your network. You are going to have to allocate real ranges. You are going to have to share those ranges somehow. So you are going to have to talk to the network team. We also don't have this nice property where it's really obvious where traffic is coming into the cluster. So you might be exposing certain services to the broader network in a flat network, or it's just something that you have to be aware of and kind of handle maybe with network policy. And I think something that is really overlooked is that IP address management is a huge issue in flat networks. So I talk a little bit about that here. I think a really common scenario is that in a data center, you may have multiple availability zones, and each of these availability zones may correspond to a different IP range. And so a requirement on your cluster is going to be that if you launch a pod in one availability zone, you need to make sure that it gets an IP from that zone's range. And conversely, if it's launched in the other zone, it needs an IP from the other zone's range. And so this is something that you really need to be thinking about if you're going to go down the flat network path. And it's kind of for that reason that I wouldn't suggest advertising service VIPs to the rest of your network. So I know that's something that some network providers will do, but there's really, as far as I know, no great way of getting good IPAM management around these service VIPs. So something to keep in mind. I mentioned previously with overlays, you may not have to talk to the network team, which should be good, but I think you should also consider that if you don't, then your options for layer 3 or layer 4 ingress are just node ports. And that may not be enough for you. So you might not be out of the woods in that regard. And even with node ports, there's some downsides, right? So you have to grab a port out of this high port range. Clients still have to find out about your node IPs somehow. So you still need some service discovery mechanism. So something to consider. The last thing I'll say is that by default, the Kubernetes controller manager assumes that you have one pod CIDR that's going to cover your entire cluster range. And out of this CIDR, it's going to kind of hand out a node CIDR to every single node that joins your cluster. On a flat network, I think this is probably too heavy-handed to work, especially if you ever want to grow your IP range, if you want to just joint IP range. That's probably not something that's going to work for you in a flat network. In an overlay, it might be okay. But again, something to think about when you're choosing your network provider. So for us, we use Calico for implementing both of these models. It does overlays, it does flat networks, and it has really good support for IPAM. So with Calico, I can say if I launch a host on a certain node, or actually if I launch a pod on a node, I can look at the node label and use that node label to determine which IP pool that pod gets an IP from. You can also do this with labels on a pod. So you can say pods with a certain label should get IPs out of a certain pool. And this is really flexible. You can get really fine-grained control here, which is great for us. It also implements Kubernetes network policies, which is good. So what are the problems that we run into? So as a bit of a background, we run both bare metal on-prem and also in private cloud VMs. We support both. And we kind of had some tooling that we could point at legacy hosts and get out Kubernetes cluster. But we have this new network architecture kind of come into view, and now our tooling breaks for networking reasons, pretty much. So what does that new environment look like, and how does it cause challenges? So on our new hosts, in this new environment, we do layer 3 ECMP down to each host. So equal-class multipath routing down to every single host. And what that means is that we have multiple independent paths to each of our hosts, which is really, really nice. We also get full throughput across 2 links. So there's some benefits for the network team in terms of maintenance. And we've also managed to kind of eliminate layer 2 domains in this model, which simplifies, again, thanks to the network team. And so that means that each host is kind of advertising its address using BGP to the 2 top rack switches. What that kind of looks like is shown in this diagram. So each host has a service IP, what we call a service IP, and that is the real address of the host. That is the address that other hosts or pods are going to be able to talk to that host on. But it's also got, on the actual interfaces, it's got 2 what we call transit addresses. And these transit addresses, you can think of them as like link local addresses. They're not going to be routable on the rest of the network. And the only thing that they're really used for is for advertising this service address using BGP to the top rack switch. So we can talk to the service addresses. We can't talk to the transit addresses. So how does that cause issues for us? Well, one thing that really stands out is that, when we look at GitHub issues or PRs, we don't see that many people that are running into the same problems that we've run into with our setup. So we're thinking that there maybe aren't that many people doing this. And so that's kind of a challenge. Another challenge is that typically your networking stack is going to be made up of these open source components. So you may have to make changes to those open source components. You may have to post hoc kind of figure out what certain implementation details are supposed to do. So why a certain iptables rule exists, or why routing is set up in a certain way. And maybe that's in the code, maybe that's nowhere, and you just kind of have to figure out on your own why that is. And sometimes people don't understand your use case. So if you go back to this slide here, this is a little tough to kind of explain in a GitHub issue. And people may not understand why you need the feature that you need. So that can be a little challenging as well. So what's the first major issue that we run into? So I mentioned before that our hosts are advertising their service addresses, their real addresses, using BGP. And they're running Bird, which is a routing daemon, to do so. So it's a process that runs and speaks BGP to the switches. Calico also makes use of Bird, which turns out to be something that's kind of hard to deal with. So they both are running in the root network namespace. They're both binding the same ports and addresses. And also, because the BGP spec, the top rack switch is only going to accept one peering connection from our host. So how do we deal with this? For the same port and same address issue, we can handle this pretty neatly by overriding Calico config templates. So in the Calico node container image, there are some templates that are used for configuring Bird and saying what the Bird config should be. And you can overwrite them either with a config map or a local file. And that can kind of let you get custom behavior in Calico that you may need for your specific environment. And also, of course, you can change the config of the Bird instance that's running for the host and for the service IP. The Tor only accepting one peering connection is a little bit tougher to deal with. So we were trying to figure out, should we even run 2 Bird instances? Maybe we could, bootstrap our host, and then once Kubernetes comes up, we could have the Calico Bird be responsible for advertising both Kubernetes pod routes and the service address. But we didn't really want to do that because, we don't really want to rely on our CNI provider to be up in order for our host to be reachable on the network. You can imagine, that would be a tough dependency to have. So, in the other direction, maybe there's some way we could have figured out how to get the host Bird to advertise Kubernetes routes, but I think that was something that was going to be a little tricky to figure out. So what we ended up doing is we ended up pairing them together. So Calico Bird, and as you can see in this this slide, Calico Bird is sharing these Kubernetes routes to the host Bird, and the host Bird's kind of acting as a route aggregator, combining them all up and advertising all of them to the top rack switch. So that's how we dealt with that. But after dealing with that, now we see that our hosts kind of drop on and off the network intermittently. And so we actually weren't really sure what was going on here. And to have an idea, you kind of have to understand how Bird works. So Bird, I think like a lot of routing daemons, works like similarly to a Kubernetes operator in that it has a desired state, which is all the routes that it knows about. And it's constantly syncing and diffing that desired state against an actual state. In this case, that's going to be a routing table. So it's going to look at all the Bird routes in the routing table, do a diff against the ones that it expects, and then either delete or add routes based on that. So a problem here is that both of these Bird instances are syncing the same routing table. They're both seeing routes written by the other Bird and saying that those routes shouldn't be there. And so they're constantly fighting for control over this routing table. So something you can do is actually sync them to separate routing tables. So I didn't know about this feature on Linux before doing this work, but the kernel actually supports up to like 250, I think, routing tables per network namespace. And you can configure how they're accessed using IP rule. So we ended up syncing them to 2 separate routing tables, and now we can run 2 Bird instances at the same time. So those were kind of the Bird issues we faced. The second really big issue is that iptables Masquerade is tough to deal with in our environment. So iptables Masquerade is an iptables target that's used for source natting, which I mentioned we need for overlay networks, but it's used in some other places as well. And what it does is it determines the address to use for that source natting kind of automatically. What it does is it looks at the address on the interface that traffic is leaving out of, and it uses that primary IP address on that interface as the source address for the source natting. So this is useful in a lot of situations, but not ours. Because if you go back to this diagram, you'll see that on our interfaces, we've got these unroutable transit IPs. And so any Masquerade rules are going to pick up those transit IPs because those are the interfaces that the traffic is actually leaving on. So this presents some challenges because Masquerade is used in a lot of different places. It's used in kube-proxy, Calico. It's used for source natting of pods. It's used for hairpin traffic. And in most of these cases, we need an iptables SNAT rule instead. And an SNAT rule allows you to specify a specific IP address to use for that source natting. But it's not all. We don't always need an SNAT. So the tricky part here is that we can't just find and replace all the Masquerades and replace them with SNATs because there are certain situations in which we do need that Masquerade to happen, typically with an overlay. So in Calico, addressing Masquerade is somewhat easy. So what we did was we modified Calico node to accept as a parameter to its config an IP address to be used for an SNAT rule. And we upstream those changes. So if anyone else is running in a similar setup, that's something that you can use. In kube-proxy, the issue is a little more nuanced. So kube-proxy uses Masquerade for more nuanced cases, right? So it's used for hairpin traffic, for traffic that's coming off cluster. But we do sometimes need the Masquerade, typically with an overlay network and a tunnel device, because the address on the tunnel device is actually the address we want to use. So we kind of have to look at each of these situations in kube-proxy kind of on a case-by-case basis. So in the course of this, we ran into something that seemed like a kernel bug. We were running in an overlay environment using IP and IP tunnels, and some hosts that were talking to a Kubernetes service VIP were doing Masquerade on the encapsulating traffic, but only to some VIPs, only on some hosts. So again, I mentioned you have this encapsulated traffic, and this is kind of the original traffic to the pod, and then we encapsulate it in another protocol, and the encapsulating packet is the one that was getting the Masquerade done erroneously. So we saw it on some hosts, didn't see it on others. And the issue seems to come and go intermittently. And we've got 2 hosts that are set up identically that seem to be exhibiting different behaviors. So it kind of looks like a kernel bug at this point, but let's dig in. So in addressing pretty much any Kubernetes networking issue, the first tools I go to are ping, dig, netcat, and an IP route pretty much. So ping for checking out routability to pod IPs, dig if seems like there's something related to DNS, netcat for testing UDP or TCP connectivity, and then IP route 2. So looking at how your routing is configured, looking at how the sockets are listening or not listening. And we ran this across both these hosts, and actually we were reproducing the issue with Netcat. So the Netcat was not able to, Netcat was what was demonstrating the issue, but all these other tools kind of, it appeared that both hosts, that, you know, the ones that were working and the ones that were not working, kind of had the same setup. So going a little deeper, you can use tcpdump. So tcpdump kind of lets you treat the kernel as a black box. You can kind of look at how traffic looks like when it goes in. You can look at how traffic looks like when it goes out. And then from there, you can kind of guess what all these Kubernetes components in the middle are doing. So it's really useful for seeing, you know, what does the network see when we drop traffic on it. It's also really useful for even seeing if traffic is on the wire. So a lot of times, if you check that first, if you check if the host is even passing traffic, you can solve the issue right there, or have a better idea of where to start looking. The second tool I'll mention is iptables. So I think it has a little bit of a bad rap, or maybe like a scary rap. But I think it's, you know, once you run through a couple of scenarios with it, I think it's not too hard to grasp, and I definitely think it's very much readable with some practice. But if that still seems a little tough, you can also use the iptables trace target, which is an iptables target that will output every single iptables rule that gets hit to a kernel buffer, and then you can kind of trace the path of packets that way. Last tool I'll mention is conntrack. So I didn't know about this tool when I started doing this work. And if I had, it would have really helped me out, which I'll talk about in a sec. But conntrack is something that will show you all the connections that the kernel knows about and all the address translation that's done on those connections. So essentially, it's just a big table of connections with the address translation that's been done on them. So all those things were kind of showing us the same behavior, or they were kind of showing us what we expected on the good metas. So again, we don't really know what's happening and what's causing this issue. So we have to go a little bit deeper. In this case, we're not even debugging the network anymore. We're kind of debugging the kernel. And so the tools I would recommend for that, at least starting out, are like perftrace. So perftrace is an strace kind of drop-in replacement, but it also gives you, in addition to the system call boundary, you can also get events that are happening inside the kernel. So there's all these trace points within the kernel that perftrace is able to show you happening. So we ran perftrace on the working and non-working hosts, and replicate the issue, and we didn't actually see a difference there. But what it was really useful for was, with these trace point events, that gives us a place to go back into kernel code and start digging into kernel code and kernel functions. So I'm obviously not a kernel expert, but using these trace points, I can get an idea of what are the functions involved in this, and where can I start looking. And using that, I can start using ebpf. So ebpf is really hot, really cool right now for CNI implementations, but you can also use it to inspect functions or inspect arguments to kernel functions on basically stock systems. You can look at return values of these functions. And so once you have a place to kind of dig in using perftrace, ebpf can give you a little bit more insight. The last tool I'll mention is ftrace. So like ebpf, you kind of need an idea of where you want to start looking first, but it's going to show you the entire call stack for a process that is using kernel code. And it'll also, if you need it, can show you every kernel function that runs on a given CPU core. So again, you kind of have to have an idea of where you want to be looking, but if you do, then ebpf and ftrace are really useful too. So what was our issue? So to understand kind of what's going on here, I need to mention that something that you may not know is that in iptables, the NAT table is only processed once per connection. So I mentioned conntrack is the table that has all these connections in it, and NAT is only done once. So every other connection that, or every other packet that is in that connection is going to use that same entry in the conntrack table. So kube-proxy is using iptables mark to select packets for masquerading. So when it does destination NAT, if that packet is going to need a source NAT as well, it'll mark that packet. And using ebpf, we were able to see that this mark persists through encapsulation. So if we had an encapsulated connection that is marked for Masquerade, then the encapsulating connection is also going to be marked for Masquerade. So this kind of explains why on the encapsulating packet, we were seeing the Masquerade as well. What it doesn't explain is why some hosts were good, why the problem would kind of come and go, and why we'd see this on some hosts and not others. So the reason for that is that the encapsulating protocol is IP and IP, which is a stateless protocol. So every subsequent encapsulated connection that is going to be used over this tunnel is going to use the same encapsulating connection in conntrack. So if the first encapsulated traffic that goes through this tunnel is marked for Masquerade, then all subsequent encapsulated traffic, even if it's on a different encapsulated connection, is going to be using the same encapsulating connection. And so all of that traffic is going to be masqueraded. Conversely, if the first encapsulated traffic that passes through that tunnel is not marked for Masquerade, then when that encapsulating connection gets created, it's not going to have the Masquerade on it. And so any subsequent encapsulated traffic that goes through that tunnel, again, even if it's on a separate connection, is not going to be marked for Masquerade. So that ended up being our big issue. And yeah, that's pretty much my talk. I thank you for listening, and I hope that you got something useful out of this. Bloomberg is hiring SREs, if that's something you're interested in, and I'll be available for questions right now.